Let's make sure that even someone with zero knowledge of general relativity can learn it within 8 minutes, whether you believe it or not. First, take a look at this thought experiment that fundamentally changed the course of human scientific progress. Imagine you are inside a small room completely isolated from the outside world. After measuring, you find that your weight remains exactly the same at 80 kilograms. Now, determine where this room might be located. 1. On the surface of the Earth. 2. Inside a spacecraft accelerating through space with an acceleration equal to that on Earth's surface, approximately 9.8 m. S3. It is impossible to determine. Let's see if your thoughts and answers surpass those of 99% of people. Now, let's travel back to the early 20th century. At that time, a low-level clerk working in a Swiss patent office happened to look out the window and saw a cleaner standing on a ladder. This sparked an inspiration and led him to ask a deceptively simple yet profound question. What if the cleaner accidentally fell off the ladder? If we disregard the upward resistance of air, would the cleaner still feel the gravitational pull of the Earth before hitting the ground? Imagine this, without the support of the ground and while accelerating downward, the cleaner would experience complete weightlessness, unable to feel the Earth's gravity. The reason is that the object's accelerated motion cancels out the gravitational pull of the Earth. This low-level clerk intuitively believed that the simplicity of this question hid a deeper truth. This question hides an astonishing truth. Accelerated motion generates inertial force. For example, when a rocket accelerates rapidly upward, it creates a downward inertial force that pins astronauts firmly to the floor. Similarly, when the cleaner accelerates downward, an upward inertial force is generated. However, this force seems to cancel out the downward gravitational force. It appears that gravity and inertial force can neutralize each other. But what is the connection between them? Can they replace one another? A thought experiment began to take shape in the clerk's mind. After much contemplation, he hypothesized, for a closed room, even if it is located on a spaceship far from Earth, as long as the spaceship's acceleration matches the acceleration due to gravity on Earth, the inertial force inside the room would be indistinguishable from gravity on the Earth's surface. Observing the unchanged weight of 80 kilograms, a person inside the room would feel as if they were on Earth's surface. In this scenario, inertial force completely replaces gravity. Finally, the clerk arrived at a bold conclusion. The inertial force formed in an accelerated reference frame, and the gravitational force around celestial bodies, are fundamentally the same in nature. They are equivalent and represent the same force. The equivalence principle, which fundamentally changed the course of science, was born. The brilliant clerk behind this discovery was, of course, Albert Einstein. At this time, it had only been a few years since he published his theory of special relativity. However, Einstein was tormented by the fact that special relativity could not explain accelerated motion or gravity. The discovery of the equivalence principle gave him a glimmer of hope, and he declared it the happiest thought of his life. Following this, Einstein conceived a rotating disk and an ordinary beam of light, which ultimately unraveled the mystery of gravity and inertial force. This rotating disk later became known as Einstein's rotating disk. Imagine a flat plane with a circular disk. If the disk is set into uniform rotation, its geometric structure, being a spatial entity, will inevitably be affected by the length contraction effect described in special relativity. Let's examine how the ratio of the circumference to the diameter, known as pi, deviates from its standard value of 3.1 for 15925 during rotation. If the rotation speed of the disk is relatively slow, you might not notice any significant change in pi. But if the linear speed of the disk's circumference approaches the speed of light, say, 99% of the speed of light, what would happen then? Since every point on the circumference is moving at 99% of the speed of light, according to the length contraction formula in special relativity, the circumference will shrink to 14.11% of its original length. The diameter, however, remains unchanged because it is always perpendicular to the direction of the rotation of the circumference. As a result, the value of pi, the ratio of the circumference to the diameter, will shrink proportionally to 0.4432 due to the shortening of the circumference. As the rotational speed of the circumference approaches the speed of light, the value of pi will get closer and closer to zero. At this point, the geometric structure of Einstein's rotating disk begins to collapse. What kind of geometric structure could allow the circumference to shrink while the diameter remains unchanged? Einstein quickly thought of a curved two-dimensional surface. Imagine drawing a circle on the curved surface of the Earth, using the North Pole as the center. The diameter would follow the curved surface of the Earth along meridians, bending downward. The diameter becomes a series of curved lines, extending from the circle center to the circumference, always perpendicular to the circumference. If you compare the circumference of a circle on the Earth's curved surface with a circle of the same diameter on a flat plane, the circumference on the Earth's surface will be shorter, and the value of pi will accordingly be smaller. This can also be understood as follows. When the circumference of the circle remains unchanged, but its diameter gradually bends into a third spatial direction, the value of pi decreases due to the increase in the diameter. At this point, Einstein realized that the rotating circle was no longer a flat geometric structure. In reality, it had transformed into a non-Euclidean geometry. In other words, the plane on which the circle originally existed becomes curved in a certain direction, as a result of its rotation. However, it is important to note that this curvature occurs in the temporal direction within spacetime. Einstein then thought of the most critical insight. The curvature of the spatial geometric structure is accompanied by the emergence of inertial forces. For example, on a two-dimensional surface rotating along with the circle, inertial forces, commonly referred to as centrifugal forces, appear. If one stands on the rotating two-dimensional surface, the farther from the center of the circle, the greater the outward centrifugal force. The closer to the center, the smaller the outward centrifugal force. Similarly, the farther from the center, the greater the curvature of the two-dimensional surface. The closer to the center, the smaller the curvature of the two-dimensional surface. Based on these observations, Einstein boldly hypothesized that the appearance of inertial forces is merely a surface phenomenon. The underlying physical essence is actually the curvature of space. When flat space becomes curved, perceptible inertial forces emerge. If curvature is used to quantitatively represent the degree of spatial curvature, in regions with greater curvature, inertial forces will be stronger. In regions where the curvature is closer to zero, inertial forces will be weaker. To validate this hypothesis, Einstein conceived a brilliant method, using the trajectory of light in a vacuum to test whether space is curved. Since the speed of light is the fastest in the universe, light in a vacuum must travel along the straightest and shortest path. In a vacuum filled with inertial forces, if a beam of light is emitted at an angle perpendicular to the direction of the inertial force, and the inertial force truly originates from the curvature of space, the trajectory of light would form a curve. Conversely, if inertial forces are unrelated to spatial curvature, the trajectory of light in the inertial field would remain a straight line. Of course, in Einstein's era, this was still a thought experiment. Now, let us imagine the interior of a spaceship accelerating straight upward. If a beam of light is emitted horizontally, as the light travels and eventually hits the wall, the entire room continues its upward acceleration. However, the speed of light cannot increase. The acceleration of the small room has no effect on the speed of light. When the light reaches the wall will have already moved upward by a certain distance. As a result, within the small room, the trajectory of the light will inevitably appear to deflect downward. If this deflection angle is magnified, it becomes clear that within the inertial field of the small room, the light's path is no longer a straight line, but a curve bending toward the direction of the inertial force. A remarkable fact emerges. This curve is actually the straightest possible line between the emission point and the point where the light reaches the wall, and it is also the shortest possible path between the 2 points. If one were to forcibly draw a visually straight line between these 2 points, it would appear shorter than the curve traveled by the light. However, in the curved space of the small room, the visually straight line would actually be longer and more curved. This is because light always travels along the shortest path between 2 points. At this moment, Einstein realized that inertial forces are indeed a result of the curvature of space. According to the equivalence principle, gravity must also be a result of spatial curvature. Thus, Einstein finally uncovered the true nature of gravity. Objects generate gravity because their presence causes the surrounding space to curve. The mass of an object measures the magnitude of its inertia. For instance, on Einstein's spinning disk, the farther from the center, the greater the acceleration, the stronger the inertial force, and the more pronounced the curvature of space. Similarly, the greater an object's mass, the stronger its gravitational force, and the more significant the curvature of space. As physicist John Archibald Wheeler famously put it, matter tells spacetime how to curve, and spacetime tells matter how to move. Modern physics holds that gravity is not just the curvature of space but the curvature of the entire spacetime continuum. This is because all objects, including light, always travel along the shortest path between 2 points in spacetime. Thus, the distortion of space inevitably causes the bending of time. If, by following Einstein's thought experiments from the beginning of this discussion, you have understood the curvature of space behind gravity, then one of your feet has already stepped into the doorway of modern physics. If you liked my video, make sure to subscribe my channel and hit the bell icon for more information. Thank you. See you next video.